So I just wanted to make a quick video on heating in perovskite solar cells, and this is a nice opportunity to demonstrate the multiphysics capability of OghmaNano. And what I mean by multiphysics is where we're considering both the optical properties of a device, so calculating generation rates and things like that. Then we calculate the electrical properties of the device, and we also link this to the temperature of the device. And with all these three things together, we can really get a good idea of what's happening in the device. And you can access this simulation from new simulation, thermal modelling, and then it's 2D perovskite FDTD Cell Heating. So this is primarily a 2D simulation. So this is the FDTD grid that's going through the cell, and we've also got the electrical simulation window in there. So let's just run this and see what happens. So the first thing to do is we need to calculate the optical generation, and we're going to do FDTD. But before we actually get to simulating the optical properties of the device, we need to do one calibration run with FDTD to effectively remove the effect of the simulation boundary conditions. And this is a standard thing to do. So that first run where it says calibration is doing that. Then we're doing solving the optical problem, and then after we've got the generation profile, we start solving the electrical and thermal problems together self-consistently. So in each one of these steps, these voltage steps, it's solving both the 2D electrical problem and also the 2D thermal problem together self-consistently. And you can see the temperature within the device that's outputted there. So that's finished. So let's look at what it's done. So let's look at the generation profile first. So here's the generation profile. So this is the generation of light that's gone into the device, and we can plot this or project this onto our 3D model by clicking the 3D mode button, and we can see the light sort of coming in from the top of the device into the bottom. And you must remember that this is absorbed photons, not the actual photon density, because we're only interested in what's absorbed. So if we plot the device on top of that, we can see how that's sort of interacting with the device. And of course that light's going to cause heating within the solar cell. So if we look at H.CSV, this is the heating within the device. And once we've got the light, once we've got the generation profile, we can do the drift-diffusion simulation. And the first result from this to look at is the JV curve, which looks like a normal perovskite JV curve, more or less. So relatively good JSC, relatively good VOC. So now we can dig into the actual electrical results in detail and try and plot those in 2D by looking at the snapshots. So let's, for example, just plot the electron current and the hole current. There's a whole current, and we can sort of step over those as a function of voltage and see how they change as we apply our voltage ramp. We can also see how the temperature evolves within this structure by plotting T lattice. There's T lattice, and we can see effectively we've got some sort of temperature gradient across our device. So not only have we simulated the optical properties, we've also simulated electrical properties and also how this is bound into the heating effects. And lots of electrical parameters are very sensitive to heating effects. So sometimes this is a very important thing to model, and it sort of shows the coupling of these effectively multiphysics parameters. What else is worth looking at? So I think that's just a quick demonstration of using those three models together, and I think I'll leave it there. So thank you very much for your attention.